Okay, we're going to go through here a very basic Bernoulli's equation, which is actually one of the simplest, and that is just a place where essentially pressure energy per pound of material, P over gamma, trades off to be velocity energy. And that occurs anytime more or less you've got a breach in a pipe or a breach in a system where you've got a pressure tank and then it starts flowing out of a hole, even a pipeline, but it's especially a hole. So we'll try to do this with this kind of rough mouse, but we'll see how we can do. Here's the problem statement. Consider a 12-inch diameter steel pipe, ductile iron pipe, through which water inside is a velocity of 0, but there is an internal pressure of 60 psi. What will be the flow rate, Q, in cubic feet per second coming out of that hole or tap of 5/8 inch diameter if one assumes a discharge coefficient of 0.62? And that discharge coefficient is just something that you multiply the velocity head by to get the loss of energy through the pipe or through the hole. Right away, you write down and chant Bernoulli's equation, and you also realize that very often to get a flow rate you need to get the velocity and then multiply by the area. You then, and this is where I'll start trying to use this mouse here, use the pointer options, felt tip pen. You have to realize a couple of things here. If you assume this is 0.1 right here, you know, more or less someplace in the pipe, and 0.2 is just something in the water stream, just a point right there in the water stream, so we'll call that 0.2. Now you've determined your 0.1 and 0.2, and you can start right away after you write and chant Bernoulli's equation. You can all of a sudden, well, boy, y1 product 1 equals y2, and then eventually you can realize that because of the ratio of the diameters here, 12 inches to 5/8 inch, that the velocity here coming through that pipe is going to be pretty much nil. And so you can cross those out. And then you can realize that you are in an open stream here. The water's flowing out and it's subject to atmospheric pressure, and so you see the pressure there falls out. And then what you're left with is essentially the pressure in the pipe being converted to either the energy leaving or the head loss of the energy lost. And if you remember now, the head loss is equal to a velocity head, in this case v2 squared over 2g times some coefficient. Now this case that coefficient is right here, 0.62. And so you can immediately see that essentially this is a square root of 2gh problem if you just recognize it, and eventually you'll see it's just the square root of 2gh times the discharge coefficient. But by going through Bernoulli's equation, you have to now realize how important the unit thing is, and you need to convert everything to feet, pounds, and seconds. And that would mean that you need to convert 60 psi to feet of water, and you need to convert eventually that 5/8 inch diameter to feet so you can get a area to plug into this equation. Alright, so 60 psi, how do you convert it? Well, if there's not a datum shift, you know that you can convert it by any number of ways, but many of you very quickly should be able to do 60 psi pounds per square foot and multiply by 1 of 144 pounds per square inch. I'm going to put this here, pounds per square inch, by 144 square inches, over 1 square foot. You multiply by 1, or you, if you need to, use the pressure converter calculator in your program in your calculator. But in this case, you should be able to convert 60 psi to PSF, and you get 8640 PSF. $86.40. But many of you are probably realizing right now, I don't even need to do that. That's PSF. Because what I'm not interested in is not the pressure, but the pressure head, which is 8640 divided by 62.4, which is going to give me feet of water, which should have been just that conversion of about 40 feet of, I'm sorry, there's 33 feet of head for every 14.7 psi, so that should be about 140 thereabouts. Let's see what that turns out to be. 8640 divided by 62.4 is 138.46. So what you end up with is this. The head of 138.46 is going to be equal to 1 plus 0.62. In other words, you're going to take and factor out v squared over 2g, this being the 1, this comes to the 1, and then the head loss discharge coefficient 0.62 puts in there, and you got v squared over 2g. You solve for velocity by taking 138.462 divided it by 1.62 equals multiplying it by 2, multiplying it by 32.2, and you take then the square root, and you get a velocity of 74 feet per second. Which of course doesn't get you the answer. You want the Q rate, and you need to know then the area. The area of a 5/8 inch diameter pipe would be the square of the difference from a 2-foot diameter pipe multiplied by pi. So let's look at that. 5 divided by 8 divided by 12 gets me feet. That divided by 2 squared times pi gets me an area of around 0.002 depending on your float, times 74 gets you a flow rate of 0.158 CFS. 0.158 CFS. Now I'll run that out on a calculator, but let's realize that a problem like this is, except for the algebra, is solved by doing Bernoulli's equation, writing 2 points that you know something about. In this case, you know the elevations are the same, and you know the velocity essentially through here is pretty much close to 0. Therefore, you have the pressure being converted to velocity because it is freely discharging, and then you have the head loss there, which is proportional to a coefficient of discharge. So we end up with a flow rate of 0.158 CFS. I'm going to end the show, keep the discharge, and